Good day, class. We are going to discuss geothermal power plant. Okay, so geothermal power plant or the geothermal energy. It is the internal heat of the earth. So the source of power is inside the internal heat of the earth. So for centuries, geothermal energy was apparent uh through Earth's crust, no, allow heat from Earth's molten core to venture close to Earth's surface, such as the volcanoes, geysers, fumaroles, and hot springs. And our most visible surface manifestation are through smoke. No? So geothermal energy has been used for centuries, where it is available for aquaculture, greenhousing, industrial process heat, space heating, so it was first used for electricity production in 1904 in Italy. Okay, so basically, uh, the geothermal energy is harnessing internal heat from the Earth's crust or from Earth's crust and mantle, and it is sustainable and renewable because there's no depletion for geothermal. And also, it has a diverse application uh, through power generation, heating, cooling, and a variety of industrial processes that gives a versatile energy solution. Okay, so there are geothermal classifications that are basically divided into three basic classes. So we have the hydrothermal convection resources. We have the hot igneous resources, and then we have the conduction-based resources. Okay. So under the hydrothermal convection resources, we have the vapor dominated and the liquid dominated. Okay. So for the hydrothermal convection, um, these are all included that are formed underground reservoir from the Earth's heat towards the surface by convective circulation of water, either the circulation of water or the liquid dominated resources, or the steam, which is the vapor dominated resources. Um, so for the hydrothermal resources, the vapor dominated, the temperature characteristics will be about 240 degrees Celsius for the vapor dominated. And then while the liquid dominated is a subclass, it is sub to three classes. We have the high temperature liquid dominated, the intermediate temperature, we have the low temperature. So for the high temperature, we have a range of temperature of 150 to 300 degrees Celsius. For the intermediate, we have 90 to 150 degrees Celsius, and the low temperature would be less than 90 degrees Celsius. So for the vapor dominated resources, so in the vapor dominated hydrothermal system, it is boiling of deep subsurface water that produces vapor. So which is also often known as the superheated by the hot surrounding rock, no? So uh, geologists actually speculate that the vapor moves toward the surface with a level of cooler near surface rock that may induce condensation, so which along with the cooler groundwater from the margins of reservoir. Okay, so uh, basically the vapor dominated resource is uh most of it are steam, no, it is actually the ideal uh for geothermal because we do not need to convert water to steam because it's already dry and saturated steam, no. So while in comparison to the liquid dominated resources, of course, this is how hot water or wet system hydrothermal resources. So these are more commonly found than dry steam deposits. So most of the geothermal resources uh, are liquid dominated. So they had this hot water system were often associated through hot spring, which discharges at the surface. So when wet steam deposits occur at the considerable depth, the resource's temperature is often well above the normal boiling point. So like what I told you, these are uh the ranges of temperature for the hydrothermal convection resources. So we move on to the other resources, which is the hot igneous resources, or it is a rock intruded in a molten form from depth. No depth, no. So we have subclasses of the hot igneous resources. We have the part still molten, or the magma system, which the temperature is higher than 650 degrees Celsius. And then the other class of the hot igneous resources is not molten, so or the hot dry system, the hot dry rock system. The temperature ranges from 90 to 650 degrees Celsius. So the temperature in this buckets it increases with depth and also the proximity to the magma chamber. But because of the impermeable nature, they have a lock water aquifer, so they are often referred to as hot dry rock deposits. So these are the other resources, and then lastly we have the conduction dominated resources. The conduction dominated resources are heat carried upward, so by conduction through rock. So we have the subclasses. We have the radiogenic, the sedimentary basins, and the geopressured. So radiogenic, which ranges from 30 to 150 degrees Celsius, these are heat generated by radioactive decay. So that's why this is radiogenic. No, and the other one is sedimentary basins. These are hot fluid within sedimentary rocks. No, and lastly we have the geopressure, which is the hot fluid under high pressure. Okay. So for the geothermal power plant designs, we have the dry steam or the direct steam conversion. We have the flash steam with hot water, okay, and then the binary cycle. So later I will show you the components of the schematic diagram of those power plant design. So for the direct or the dry steam or the direct steam conversion, so these are the usually vapor dominated are suitable for this dry steam or the direct steam conversion. So it's a natural pressurized steam already, which is piped from the well to a power plant where it expands through a turbine already, a turbine generator to produce the electricity, no? Okay. So from the turbine, the steam is exhausted to the condenser, and then the condenser and it's condensed to its liquid frame and pumped from the power plant. Okay. So usually the condensate is reinjected to the subterranean aquifer. But unfortunately, vapor-dominated geothermal resources occurs infrequently in nature. Okay, so not so much. Okay, so but we have a lot. The next power plant design is which is the flash system. So most geothermal resource produce not the dry steam but pressurized two-phase mixture of steam and water. So predominantly mostly is water. So the majority of the geothermal power plants currently operating at a liquid dominated resources which use a flash system or the flash steam energy conversion process. So uh when you say flash steam, we have flash vessel, which are often used in the flash steam to improve the plant efficiency. So the it separates the steam and the water in that flash. Okay, so later I'll show you what is the basic schematic diagram for the flash steam. Okay. So of course the binary cycle, these are the alternative approach to flash steam plants for electric power generation at liquid dominated geothermal. So in this type of plant, we have a secondary fluid. Usually it is of fluorocarbon or hydrocarbon, which is used as a working fluid in a Rankine cycle. So the geothermal brine is used to heat the working fluid. So that is a binary process. So a binary process may be attractive alternative to a flash steam process and the geothermal producing high salinity brine. So since the brine can remain a pressurized liquid state throughout the process, and also it doesn't pass through a turbine, problems associated with salt precipitation is scaling as well as the corrosion and erosion are greatly reduced. No, so these are for the binary. Okay. So the advantage, of course, of the geothermal, it is renewable and sustainable. So like what I told you earlier, there's no depletion of the geothermal resources. So of course, this is friendly also because it has a less greenhouse gas emission compared to your traditional fossil fuels. Of course, it is reliable and consistent, not like solar and wind. Solar depends on the sun and wind depend on the wind. So for geothermal, there's always heat coming out from Earth's core, no? So it is also cost effective, cheaper to uh, to operate. Okay. So, but there's a challenges and limitation. We have the site selection. So you need to have or to identify a suitable geothermal reservoir with a sufficient heat with the ranges that is needed to have a geothermal power plant. So you also have a front cost which in drilling and constructing geothermal power plant. So it can be a limitation also or disadvantage. So and also environmental control through seismic activities or earthquake, geothermal is prone because it's already under attack under Earth's crust, no? So it anytime it might have this activities and accidents, no? So the environmental impact of geothermal is low emission, lesser water usage, and small carbon footprint. Okay, so the future of geothermal will be so the technological advancement by the EGS or the enhanced geothermal systems. Of course, the policy and incentive of each government to have a geothermal adoption, a widespread adoption of geothermal uh, power plants, no? And also uh, to have to be an alternative to renewable also like the solar and the wind. Okay. So the cost of building geothermal power plants for the exploration and the drilling, it's around 50% of the cost, while the power plant construction, 30 to 40% of the total cost. The internet connection and transmission will be 10 to 20%. Operating and maintenance around 1 to 2 cents per hours. No? So the geothermal power plant in the Philippines has a lot of potential, no? So Philippines is one of the leading geothermal producers, which significant in the Philippines because we are under or we are in the Pacific Ring of Fire. So that's why it's a very good potential for the Philippines, no, to enhance the geothermal power plant. So we have currently 1,900 megawatts, which we rank second in the world Okay, so the future expansion, it we can have almost double of the current one that we have. By 2030, we'll be able to have 3,400 megawatts. So these are some of the formulas that we are gonna use in solving geothermal power plant problems. So we have the mass flow stream, which is mx multiply is equals to the quality of the steam multiplied the mass. Okay. Turbine output, we have the work turbine is equals to mass of the steam multiplied by H3 minus H4, or the enthalpy 3 minus enthalpy 4, uh, multiplied by the turbine efficiency. So for the generator output, we have double gen is equals to ms times quantity H3 minus H4, multiplied by the turbine efficiency and then the generator efficiency. So we also have the heat rejected equals to ms equals quantity H4 minus H5, and overall plant efficiency is AC, or turbine output, over mgh. So these are some of the formulas that we are going to use. Okay. Okay. So we solve. Okay. So just now we will have a simple schematic diagram. No? So for a direct steam, or for the dry saturated uh, geothermal, no? So we have the turbine, and you have the generator. So we have the condenser. So you have the cooling tower. And then the production steam. Okay. So this is a simple schematic diagram. So this is the condenser. This is the turbine, the generator, and the cooling tower. So this is direct steam, or the dry steam, or the steam dominated conversions. Okay, so this is for that one. So for the binary, sorry, for the flash steam, so we have here the separator. Then it will be here. It goes to the also the the turbine, sorry, turbine, and then the generator. And then after that, we will have the direct contact condensate. So from here, sorry, I forgot the liquid plus the mixture from the production well. So this one goes to here, then to the separator, and then there we will have two ways. We have one goes to the turbine generator, and then the other one goes back to the reinjection wells. Okay. Then after that, the turbine generator, it goes to the condenser, and then the condenser goes to a circulating water pump that transports to the cooling tower. So after this, you have this that goes to the cooling tower. Okay, so this one goes to here. Then it also uh re-injected to the well. Okay, this is for a single flash, no? So if it's two stage flash system. So we have another flash here, just another one. And then that would be the two-stage flash conversion. Okay. So for this is the schematic. So for a binary, we had an heat exchanger. So this one heat exchanger that the it goes out and goes to your turbine and then the generator. And then it goes to the condenser. And then this condenser goes to the cooling tower and goes up and goes back to the condenser. Okay, so this is for the from the production brine. This is from the condenser. And then this one goes to the turbine. And this one goes to the reinjection brine. Okay. So these are just the basic uh, schematic diagram for geothermal power. Okay, let us solve. So the mass flow rate of a groundwater in a 30 megawatt geothermal power plant is 170 kilograms per hour. And its enthalpy is 1,200 kilojoules per kilogram. So if the quality after throttling is 25% and the overall plant efficiency is 20%, what is the mass flow rate entering the turbine? Okay, so from there, we can know the mass flow rate through our formula, which is ms equals to x times the gas. So we don't have mg. So we can get the energy through the overall plant efficiency, which is E plant, is equals to the turbine output all over mg H1. So for overall plant efficiency, it is given. So you just equate it. You have 20%. So 0.2 is equals the turbine output is 30 megawatts. So 30 megawatts over mg h. So mg is the one we're looking for. H1 is 94.7. So the mass is 500. So 30,000 divided by 94.7 divided by 2. So each one is, sorry, it's not 94.7, it's 1,200, sorry. 1,200. Okay, so calculated. So it's 11 mg is equals to 11.36 kilogram per second. Okay, next. In a geothermal power plant, mass flow rate groundwater is 5,000 kilograms per second. Um, the quality after the throttling is 50%. If the turbine is 50 megawatts, compute the change in enthalpy of the inlet and outlet of the turbine. So we have the work that the turbine is equals to ms multiplied by delta H, or the change in delta. So you have the one turbine is 50 megawatts equals to the mass and steam you have uh point. So you have 5 multiplied by 5,000. So delta H would be equals to, so 50,000 divided by zero point 0.5 divided by 5,000. So that would be 20 kilojoules per kilogram. Okay. So thank you. So you do this uh as your practice problem. So I'll give you two. So you have the first one. So the first one is the vapor dominated geothermal system is supplied with a saturated steam at 3 megapascal. The steam enters the turbine at 0.5 megapascal and exits at 15 kilopascal. So the turbine isentropic efficiency is 80% and the electrical generator is 95%. If the injection occurs at the cooling tower, analyze the system performance. What flow rate is required for a power generation? Okay, so the next practice problem, you have the geothermal power plant is supplied with water at a well bottom temperature of 225 degrees Celsius and a pressure of 8 megapascal. So the fluid flows into a flash separator maintained at 40 kilopascal. So the turbine exit pressure is 10 kilopascal. So the overall efficiency of the turbine mass flow rate required for an output of 0.85 determine the mass of steam from an output at 16.4 megawatts. Okay, so the answer for this is 100 kg per s. This one water is 355.8. Okay. Okay. See you. Thank you.